Welcome back to our channel. Today we will differentiate exponential functions. First, we'll prove that the derivative of e of x is e of x itself. Then we'll generalize to a of x, where a is any positive constant. Finally, we'll apply the chain rule to more complicated exponential functions. First of all, what is e? The base e is a special number in mathematics. It comes from the limit of compound interest and it has the unique property that its own derivative equals itself. That's what makes e to the x so important. So we are going to start with the derivative of x. Let's take it as example 1. What does it say? Differentiate e to the x. So we are going to perform this differentiation using the first principle as we did in previous examples. The first thing to do is to recall the first principle. What does the first principle say? It says the derivative with respect to x of e to the x is the same thing as the limit as h tends to 0 of e to the x plus h minus e to the x all divided by h. So in this question, the first thing we need to do is to calculate our individual terms. We'll start with the term e to the x plus h, and this simplifies to e to the x times e to the h. Now calculating our numerator, which is e to the x plus h minus e to the x, this gives us e to the x times e to the h minus e to the x. Identifying these two terms, we notice that we have e to the x, which is common in both terms. What does that tell us? That tells us that we can factorize out e to the x in both terms, leaving us with e to the x in bracket, e to the h minus 1. We then take our numerator and divide by the denominator h, that is e to the x plus h minus e to the x divided by h, leaving us with e to the x into e to the h minus 1 divided by h. Apply limits on both sides. We have the limit as h tends to 0 of e to the x plus h minus e to the x divided by h, which gives us the limit as h tends to 0 of e to the x into e to the h minus 1 divided by h. We can then factorize out e to the x or bring e to the x out of the limits. Why? Because e to the x is a term which does not depend on h, which is the variable of our limit. This then leaves us with e to the x times the limit as h tends to 0 of e to the h minus 1 on h. It is good to note that the limit as h tends to 0 of e to the h minus 1 on h is a standard limit which gives us 1. I'm not going to explain or derive this limit here, but this might be done in a further video. So we are just going to use the limit as it is. Substituting this limit in our equation, we then have the limit as h tends to 0 of e to the x plus h minus e to the x on h. This then gives us e to the x times 1. So what can we then conclude? We can then conclude from this that therefore the derivative with respect to x of e to the x gives us e to the x. Now moving on to our next question, given that we didn't have a term e to the x, but we had a general equation of the form a to the x, where a is any positive real number, what do we do in that case? That is what we are going to tackle in our next question or our next example, example 2. Example 2. What does this example 2 state? Differentiate a to the x. So what is the first thing we're going to do in this case? We'll say let y be equal to a to the x. Using our knowledge of algebra and logarithm, first of all, we're going to apply the natural log, that is ln or log to the base e on both sides, leaving us with ln of y equal to ln of a to the x. Now we are going to apply the base e on both sides, that is e to the power ln of y equal to e to the power ln of a to the x. We all know that e to the ln or log to the base e of y, which is this, is equal to y. What does this imply? This implies that y is equal to e to the power ln of a to the power x. This power can then be brought behind here, leaving us with e to the x ln a. If you look at this, this can still be written as y being equal to e to the x all that to the power ln a. When you look at this structure, you notice that this structure resembles a function of a function. And what does this tell us? This tells us that in order to differentiate this, we need or we can apply the chain rule. But applying the chain rule comes with a certain number of steps you need to follow. What is our first step? Identifying our inner and outer function. Let's call f our outer function. So what is this outer function? F of u, which is our outer function, is the function u to the power ln a. Now we need to calculate f prime of u, which is ln a times u to the power ln a minus 1. Recall the power whole. This can then be simplified to ln a times u to ln a times u to the negative 1. What is the next step? We need to identify our inner function. Our inner function, which we are going to refer to as g, is going to be the function g of x equal to e to the x. Now we need to calculate the derivative of this inner function, which is g prime of x. So what is g prime of x? G prime of x, which is equal to the derivative with respect to x of the function e of x, it is going to be equal to e of x, as shown in our first example above. Now, recalling the formula for the chain rule states that the derivative with respect to x of a function f of g of x is equal to f prime of g of x times g prime of x, which is same thing as f prime of u times g prime of x. So what is our next step? We need to substitute u with g of x. This implies that f prime of u, which is equal to f prime of g of x, which is equal to f prime of e of x, is going to be equal to ln a times e of x to the power ln a times e of x to the power negative 1. This gives us ln a times e to the x ln a times e to the negative x. Now, substituting g of x in this formula, this implies that d with respect to x of our complete function, which is e of x to the ln a, e of x to the ln a gives us ln a times e to the x ln a times e to the negative x, that is our f prime of u, times our g prime of u, which gives us e of x. This then simplifies to ln a times e to the x ln a times e to the negative x plus x. These two simplify to e to the 0, which simplifies to 1. This then simplifies our whole equation to ln a e to the x ln a. what can we then conclude? We can then conclude that the derivative with respect to x of a function a to the power x gives us ln a e e to the x ln a we and case or box our answer. So when the exponent is not just x but a function of x, we apply the chain rule, that is differentiate the exponential normally, then multiply by the derivative of the inside. This can be written as in the forms. We are going to write this as a general rule, that is if y is equal to e to the g of x, comma, then y prime is equal to e to the g of x times g prime of x. And if y is equal to a to the g of x, comma, then y prime is going to equal to a to the g of x ln a times g prime of x. We encase our method. So in the next lesson, we'll do logarithmic differentiations. We will prove that the differential of ln x is equal to 1 on x, generalize to logs and other bases, and apply it to tricky problems like x to the power x. Thank you. See you in the next video.